In this part of the podcast, I'll talk about input and output in Haskell. And there's one thing that one really needs to have in mind, is that Haskell is a purely functional language and that there are no side effects. No side effects at all. There are some functional languages that have side effects, namely the languages of the ML family. SML and OCaml and F# have side effects, but Haskell has no side effects. However, input and output, they're usually thought of as operations that change the program state. How can we handle state change? Now that's a very good question, and the designers of Haskell had to find a way to deal with that. The answer to that is to use something called monads. I'm not going to talk about monads in the full generality here, but monads is a concept that lets us talk about notions of state in a setting like that of Haskell. The important notion here is that of I/O actions, and we think of an interactive function as a function that will change the world. So we introduce a type called I/O. The type I/O is the type of functions from world to world, where world is some suitable type, and expressions that have type I/O. If E has type I/O, then E is called an action, and actions can be composed. Actually, programs can produce a result of type A, so in fact what we would want is that it's not I/O that we're after, but we are out to get a type I/O parameterized with some type A. So those are functions that take a world and produce something of type A and a different world, a modified state of the world. We're now going to describe three basic I/O actions. There's an I/O action called getChar, and it has type I/O of char. And getChar reads a character from the keyboard and echoes it to the screen and then returns the character as its result value. And the definition of getChar is built into the Haskell system. So there's no need to worry about the precise definition of getChar. It's there for us to use. There's also another I/O action that's really useful. If getChar is used for reading characters, there's also putChar. And putChar is a function that takes a character and returns an I/O action. I/O of nil. Here, nil or null, as it's called, is the type of tuples with no components. And putChar is also built into the Haskell system. The last I/O action that I'll mention is return. And return turns a value into an I/O action, so its type is polymorphic. It's A to IOA. And return is particularly useful when we want to finish a sequence of actions, so we can then compose a sequence of actions with return. There's something that I have to say at this point, and it's a warning. It's a warning to lovers of C and C++ and C#, etc. Return is not, and I must emphasize, not a return value statement. It is not a return value statement. There are no statements in Haskell, for one thing. It's a construct that encapsulates a term as an IO action. That's what it does. Now we can compose IO actions. We can compose a sequence of IO actions into a composite action, and we do that using the do notation. Typically this looks as follows: do, and then the first IO action B1, A1, B2, A2, where the A's are actions, VN, AN, and then at the very end we'll have a return IO action that calls a function perhaps of V1 up to Vn, may just be a return of the empty tuple. All of these expressions, they're called generators, and you've seen these before. You've seen these in list comprehension. The generator tells us where the variable vi gets its value from, and here the value vi will get its value from the IO action AI. So that's how you can compose IO actions. The notation makes you think of imperative programming, but it's not imperative programming. Everything here is purely functional. Let's have a look at what you can do with these IO actions, and it turns out that you can do quite a bit. Let's use the IO actions that we have now to build something a little more interesting. Let's write a function, getLine, that can read an entire line. Actually, that's already built into Haskell, so I'm going to redefine it. getLine prime is our implementation of that. And what is getLine prime? Well, it's a composition of IO actions. So what do? Well, we read a character, bind it to W using getChar. So we get a W, and then we ask, what is W? So the intention is that if W is a line break, then we return the empty list of characters. Else, if it's not a line break, then we have another composition of actions. We do the following. We read some more characters by calling getLine prime recursively. So we bind getLine prime, the result of getLine prime, the value of getLine prime, to XS, and then we return a list consisting of the first character W that we read and the list of the remaining characters that we read as the tail. So we return that. Let's see what that does. Yes, that works fine. We can get by, and what will happen if we call getLine prime and we type in horse? Well, then horse was read in by getLine prime, and we return the string horse. So this works fine. getLine prime and putLine prime are actually built into the Haskell system, but we could define them ourselves if we wanted to. Here's another small example. A tiny dialog written in Haskell. I'm going to define main to be the composition of the IO actions. Get a line. We've seen how we could do that with getLine prime, but here we're using getLine that's built into Haskell, and bind the value of getLine to W, and then we put line, and the function that lets us put a line is put string line, and we then put you wrote concatenate it with W, and the final IO action of this composition is return the empty tuple, as we often do. Let's see if Haskell likes that. Haskell loved that. Let's call main. What does main do? Well, we'll type in horse. You wrote horse. Our program tells us you wrote horse. So we can build dialogues using IO actions. And this is actually a very simple template for how one could actually go about doing this sort of thing.